Okay, so today we're going to look at dissolution solubility. Our syllabus outcomes, they're going to be describe and analyze the processes involved in the dissolution of ionic compounds in water. And we're also going to conduct an investigation to determine solubility rules, predict and analyze the composition of substances when two ionic solutions are mixed. For example, those particular ones listed there. So let's just have a look at some revision. So from last time, remember, to calculate the concentration of hydrogen ions or hydroxide ions at equilibrium, we need to use an ice table. We always use the ice table assumption. Okay, that's not just true for acid-base equilibria, but it's also true for pretty much everything we're doing. We also need to use the pH-POH equations, which were POH is negative log 10 OH minus, pH is negative log 10 H plus, POH plus pH equals 14. We also needed to know those other ones, so pKa is negative log 10 Ka, pKb is negative log 10 Kb. Now, dissolution, what do we mean by dissolution? So that's basically when something dissolves. Okay, so when we mix sodium chloride into water, it dissolves. That process is called dissolution. But how does that actually happen? So why is it that sodium chloride, or how is it that sodium chloride placed in water dissolves? So first, let's have a look at an example. We've got a tiny little salt crystal there, made up of ionic bonds between the sodiums and the chlorines. Now remember, our ionic bonds are an electrostatic attraction. We have positive and negative being attracted towards each other. We also have water with some hydrogen bonds between the delta positive of the hydrogens in the water and the delta negatives of the oxygen. So again, it's an electrostatic attraction between a positive and a negative. In this case, it's not a full formal positive and not a full formal negative, but it is that it's still positive and negative charge. Okay, and so we've thrown our salt into water. The first thing that happens is those hydrogen bonds between the water, they break. Okay, they're not official full bonds, they're intermolecular forces, but they break, and to do that they need to absorb energy. And suddenly they're not oriented like that, they're just all kind of random. What happens next is those water molecules then arrange themselves around one of the atoms. Okay, because they've got chlorine on the top corner, we're going to first go after chlorine. So a few of those water atoms will come in and form a little shell around the chlorine. Now you notice with the waters, the delta positive hydrogens are actually pointing in towards the negatively charged chlorine. Okay, and this is what helps it all go into solution, because we're taking that really strong electrostatic attraction between the positive sodium and the negative chlorine, and we're kind of breaking it down by having the waters face in and negate some of that negative charge. And what that does is it breaks the ionic bond. And again, energy is absorbed in that process. This is called a solvation shell. So when we have a shell of water around an atom or a molecule, it's called a solvation shell because it helps it dissolve in the water. That then comes off. Okay, so that solvated atom then goes into solution. The process then repeats. Okay, so we're repeating it for sodium. But now if you have a look at the way that the water is oriented around the sodium, the delta negative oxygens this time are facing in rather than facing out. And that's because, again, we're trying to negate that positive of the sodium with the delta negatives of the water. And so that sodium is now solvated, it now goes into solution. And that's basically our process of dissolving. Now, why is it that some compounds like sodium chloride will dissolve in water, but similar compounds like silver chloride won't? It's basically because the energy needed to break the ionic and hydrogen bonds is greater than what's released when that solvation shell forms. So I should have mentioned that a bit before. I must have missed it on the slide. When the solvation shell forms, we get a release of energy. Okay, so after the ionic and hydrogen bonds are broken, that's kind of like our activation energy. We're going up to that transition state. When the solvation shell forms, it drops back down. Now, if that process is exothermic, it's actually quite a good, it dissolves quite well. If it's endothermic, it doesn't dissolve as easily. Now, our solubility rules. So there are some rules that help us to determine if a salt is going to be soluble or not. Generally, nitrates, acetates, salts with group 1 metals, so our alkali metals, salts with group 17 non-metals, so our halogens, sulfates and ammoniums are all soluble with a couple of exceptions. Now, that itself is going to be hard to remember, so we have a nice little mnemonic. We call it NAGSAG. Okay, nice and easy to remember. Now, what does NAGSAG stand for? Well, firstly, we have nitrates, we have acetates, we have group 17 halogens, we have sulfates. So they're all the negatively charged ions that are soluble. A and G, we also have the positive ones, ammoniums, and group 1 metals. So all of these are soluble, regardless of what the other pair is, except for a few exceptions, which I'll get to in a sec. Yeah, it doesn't matter what the other one is, it's going to be soluble. So nitrate, regardless of if it's a group 1 metal nitrate, so sodium nitrate is going to be soluble. Copper nitrate, soluble. Iron nitrate, soluble. Whatever you put as the positive, if it's got nitrate as the anion, it's going to be soluble. Same with acetates. Ammoniums and group 1 metals are the same, so whatever negatively charged ion you put there, it's going to be soluble. Same with the group 1 metals. So sodium something, it's going to be soluble. The only exceptions are to our halogens and our sulfates. So, firstly, for halogens and sulfates, we have this exception we call PMS. It's just a lot easier to remember than LMS. Okay, PMS is the thing that ruins these the solubility of these salts. Okay, PMS stands for lead, mercury, silver. So basically, every single halogen salt, like halogen salt, is soluble in water except for lead halogens, mercury halogens, or silver halogens. So things like lead chloride, lead iodide, mercury chloride, mercury bromide, silver chloride, silver iodide, silver fluoride, etc. They're not soluble. Okay, so that's why they're the exception to the rule. It's also true for sulfate. So lead sulfate, mercury sulfate, silver sulfate, not soluble. Another exception we have is just for the sulfates, and we call this Castro-Bear. What does Castro-Bear stand for? Well, the Ca is for calcium, the Stro is for strontium, and the Bear is for barium. So calcium sulfate, strontium sulfate, barium sulfate, they're all exceptions to that sulfate rule. Okay, so that's the part you're going to need to remember, because we're also going to be using this a lot more later. So let's go on to using the solubility rules. The solubility rules are here to help us to determine what will happen when we mix two different salts together. So what we call a double displacement reaction. So you have an anion and a cation from one salt, anion and cation from the other salt. They swap around, so anion 1 goes with cation 2 and vice versa. Now, will those salts just mix, or will it precipitate form? Well, this is how we go about figuring that out. So in the double displacement reaction below, state which, if any, compound will precipitate. So here we have sodium chloride and silver nitrate. It forms sodium nitrate and silver chloride. Now, what's going to happen when they mix? Let's have a look. Well, actually, let's have a look at products. So initially we've got sodium. That's a group 1 metal. Okay, and as we saw on NAGSAG, group 1 metals are all soluble. There's no exceptions to that one. The same goes for nitrates. All nitrates are soluble. So that that compound there, sodium nitrate, is going to be soluble. Let's have a look at silver. Or actually halogens. Halogens are soluble except for lead, mercury, and silver. Okay, and what do we have here? We've got silver. So that one's going to be insoluble. Okay, so we're going to get sodium nitrate as an aqueous product, and we're going to get silver chloride as a solid product. So sodium nitrate will remain in solution, silver chloride will precipitate. So try it yourself. So in the reactions below, state which, if any, compound will precipitate. So here's 3. So I want you to pause the video, go through each atom, and see if the pairing actually will produce a precipitate, or whether it's just going to be a solution. And if it does produce a precipitate, which one will it be? Okay, now that you're back, let's have a look. So let's go through it. Lead, we know there's an exception for lead. So lead is insoluble when it's with halogens or when it's with sulfates. But here it's with a halogen, so that one's going to be insoluble. Okay, so that one's going to come out as a solid. Sodium nitrate, we went through that one on the other slide, but the sodium is a group 1 metal. That's going to be soluble. Nitrate, it's a nitrate, so that's all going to be soluble. So that one's going to be aqueous. Let's have a look at barium. Instantly, we should know that barium was an exception for something. What was it? Let's go back and have a look. So we look at sulfates. The exception was Castrobare. So barium sulfate is an exception to that rule. So this one's going to be insoluble. So it's going to be solid. Let's have a look at lithium chloride. So lithium is a group 1 metal. So it's going to most likely be soluble. Sorry, it is going to be soluble because there's no exceptions to that rule. And chlorine is a halogen, also a group 17 halogen, also soluble, except for there's a couple of exceptions, but lithium is not one of those exceptions. So this one's going to be soluble. So that one's going to be aqueous. Looking at the last one, ammonium sulfate. So remember, ammoniums are all soluble. There's no exceptions for that. Sulfate, they're all soluble with 6 exceptions. Lead, mercury, silver, so our PMS, as well as Castrobare, calcium, strontium, barium. But we have a look, it's actually ammonium. Ammonium is none of those 6 things. So this one's going to be soluble. And lastly, we have copper hydroxide. Copper is not on any of the soluble lists. Okay, so our positive ones were ammoniums and group 1s. Copper is neither an ammonium nor is it group 1. So chances are it's not going to be soluble unless it's got something else with it that makes it soluble. What do we have? We have hydroxide. Hydroxide's not on the solubility list either. So that means this one is going to be insoluble, so it's going to be a solid. Okay. And sorry, I'll just go to the next slide where the answers are. So lead chloride was solid, barium sulfate was solid, copper hydroxide was solid. So a little bit of revision. So this is stuff that we learnt in the start of module 3, okay, where we started looking at precipitation reactions and writing out the different types of equations. So that's what we're actually going to be doing. Normally when we write a precipitation reaction, we need to write the net ionic equation. And we also need it for KSP, which is the next lesson. So when we write the precipitation reaction, we prefer to write it in net ionic form. And this just shows the ions that are involved in the precipitation reaction. So to find it, we start with our regular molecular equation, which was this. So here's an example from the last slide. So sodium chloride, lead nitrate gives us lead chloride and sodium nitrate. So we know that lead chloride is going to be solid. Everything else is going to be aqueous because it was dissolved before it reacted. Now, we can then split it up into its ions. So everything that's aqueous will dissociate, and it'll leave the ions in solution. So just like we did earlier on in the lesson where things dissolve, okay, we have that solvation shell, things go into solution as the ions. So we end up with this, okay? So we have 2 sodium ions, 2 chlorine ions, a lead ion, 2 nitrate ions, all in solution. We mix them together, we get lead chloride solid, sodium ions, and nitrate ions. This is what we call an overall ionic equation, or just an ionic equation. But what we want is the net ionic equation. So what we do for that is we cross out the chemical species that are the same on both sides. So let's have a look. 2Na+, okay, the very first reagent. It's there at the front and it's in the middle of the reactants. So because it's exactly the same, we can cross it out. 2Cl-, we can see there 2Cl- exists on the reactant side, but on the product side it's joined in with the lead and it's a solid. So it's actually changed form. Okay, it's now in a solid form. Same with lead 2+, it's there on the left hand side, it's part of lead chloride on the right hand side. So we leave those. The 2 nitrates, they're the same on both sides, so we cross those out as well. Okay, so we're just left with 2Cl- plus lead 2+, gives us lead chloride. Okay, and so that is our overall, so that is our net ionic equation. So try it yourself. Write the following molecular equations as net ionic equations. So I've given you 2 here. So there's lithium sulfate plus barium chloride gives us barium sulfate and lithium chloride. Ammonium hydroxide plus copper sulfate gives us ammonium sulfate and copper hydroxide. So again, these are just the ones from the last examples. So instead of just leaving them like that, we're going to write the net ionic equations. So pause the video here, have a go, and when you're ready, come back and we'll go through the answers. Okay, let's have a look. So lithium sulfate. Lithium sulfate, if we have a look at it, where are we? Okay, so if we write that out as the overall ionic equation, we have lithium plus sulfate plus barium plus chloride gives us barium sulfate. Now remember that's a solid, so the ions aren't existing there. Plus 2 lithiums plus 2 chlorines. So when we've got that, we have a look, see which one is the same on both sides. So lithium 2Li+, 2Li+, 2Cl-, 2Cl-. So left with SO4 2- plus Ba2+, gives us barium sulfate solid. And that's what we've got there. Now, I find my eraser. Let's have a look at the other one. So, ammonium hydroxide. So we have 2NH4 plus 2OH minus plus Cu2 plus SO4 2- gives us 2NH4 plus SO4 2- plus copper plus 2OH minus. That copper's a 2+. So again, we go through and look for things the same on both sides. So both sides have 2NH4 plus. Both sides have 2 OH minuses. Sorry, I've just done it wrong. I should have left that one as copper hydroxide. Okay. Sorry, so let's start again. So 2NH4 plus on both sides, we can cross them off. The OH minus actually becomes part of the copper hydroxide, which is our solvent. So that stays as it is. Cu2 plus also becomes part of our copper hydroxide, so we leave it as is. But the sulfates we cross out because they're on both sides. So that we then get these two reactions are our net ionic equations. Okay. So in summary, ionic solids dissolve by being solvated by water. The water molecules arrange themselves so that the negative dipole moments are pointing towards the positive ions and vice versa. And insoluble salts generally release energy by solvation. Release less energy by solvation than it absorbs to break the ionic hydrogen bonds. Now we will be doing a practical. That'll be sometime next week. Well, it'll be during one of our combined lessons. What we're going to be doing, we're going to try and predict, using our solubility rules, what happens when we mix two solutions. For instance, we could mix lithium chloride and silver nitrate, for instance, and we could see what we get from that. We try and predict that we're going to get a precipitate, and then we can actually go and test it. Okay. So that's it for today. So go on and do those questions, have a look at the prac, and yeah, we'll see you next time.